This is what humanoids looked like in 2015. And this is what they look like now. Did you see the difference? Yeah. Why are they walking like they're wearing a big smelly diaper? In the past decade, the story of robotics has completely transformed, and the new kid on the block is robot learning. Robot learning is changing not just the face of robotics, but tech in general, from LLMs to nuclear fusion power plants to maybe even the YouTube algorithm that brought you to this video. I'm going to show you why robot learning is fundamentally different than algorithms of the past, and how it's actively shaping our future today. And more excitingly, we're going to answer the question, why are these robots about to shit their pants? This is Every Flavor of Robot. This is the first episode in a series we're creating about robot learning, where our end goal is to train our own robot dog to walk around our studio. Not only would it be a massive flex to do that, but it's a huge step in building robots that can exist and interact in spaces that were primarily designed for humans. But before we get there, let's start with a simpler problem, one that'll also help us understand the question in the title of this video: balancing an inverted double pendulum. When we say pendulum, we're really just talking about a pole that can pivot on one of its ends. It's inverted because we're trying to balance it standing up. And finally, the double just means we stack two of these pendulums end to end and try to make those balance. We actually printed our own and tried to balance these ourselves, and I was honestly surprised at how hard it was to even get one of them to balance. They're topping this in the machine shop. The butter knife press fit.
Oh yeah, the precision butter knife.
Yeah. Oh, it's pretty good. Now we just need another one.
There's no way your robot will be able to do this.
Dude,
It's too hard.
I think so too, honestly.
This is impossible.
Oh? Yeah, I think so. 1 point.
I can almost get it in this state.
How'd you get it to hit itself?
I don't know.
Yeah.
That's not even possible.
It like feels good.
Until it doesn't. I feel like I've seen simulations of these and I never believed that they would go crazy.
Yeah, I agree with that.
You can see the gears turning.
The face of concentration.
Oh, that was close. How many pendulums have you balanced in your life?
Double? Well, I've balanced plenty of pendulums.
Okay, close.
I think it's because the links are too close together, or like they're too close to the same.
Yeah, sure.
Oh my gosh, it's balancing. How are you doing this? It's actually balancing. Oh, can you transition it to the bottom state? No, okay, we still need to work.
Got it!
The double pendulum is a great starting point because it introduces a lot of the same problems as walking for a robot dog. Balancing the double pendulum requires a really complex series of actions timed perfectly correctly. If the timing is wrong or the action you take is wrong, the pendulum almost always goes into these crazy chaotic spirals. And switching between the different balancing points, with both of them standing up or one of them standing up, is even harder. In the past, we've tried to solve hard robotics problems using math, by creating descriptions or models of the robot and the environment around them. And in theory, this works great because the robot can then use those models to compute what the best thing to do would be to achieve its goal. But in practice, there are several major drawbacks to this approach. Let's say we were trying to build a model for walking for a robot, for example. The model might include the weight of the robot, the friction between the foot and the ground, and the angle of the floor. So far, so good. But now let's say the robot is carrying a box. It needs to account for how the weight of the box affects where you might need to place your foot, while also considering the friction and everything else. And now, let's say the robot is carrying something you don't want to spill. You need to make sure the robot doesn't step too hard to avoid spilling. And what happens when you accidentally step on a slippery spot and your friction estimate was wrong? How does your robot recover while not dropping the box or spilling the water? And now, forget about robots. In the case of nuclear power plants, not even our best scientists know all of the math to describe how they work. Every time you add another variable to these models, the complexity of the model increases exponentially. And when robots are out in the wild, the number of variables you have to consider makes this impossibly hard to implement. What if robots could learn to intuitively complete tasks and make decisions and solve problems just like humans do? We've spent the last 50 years trying to get robots to learn like humans, and recently, that theoretical pursuit has turned into very very real tool that's making huge waves today. Okay, this is all crazy and big and open-ended, and we haven't even touched the shitting robots. Let's get an example that'll make all of this way more clear. Let's get our robot to learn how to balance the double pendulum and switch between all of the balance points. This video was made in part thanks to our sponsor PCBWay, who are fundamental in our prototyping process. In our next videos, we're going to be bringing our reinforcement learning agents into real life, including on a robot dog. And the robot controller we're using is our own custom design, the MotorGo. Designing the hardware and the software on projects like these is a huge undertaking, and PCBWay was instrumental in prototyping our MotorGo and getting it to the point where we can trust it to do what it needs to do so that we can focus in on software tasks like reinforcement learning. If you are working on projects involving 2 to 32 layer PCBs, 3D printing, or CNC machining, you should definitely check out their services. And click on the link in the description to let them know we sent you. Concretely, the goal of robot learning is to solve sequential decision-making tasks. For our robot, the sequence of decisions is deciding which way to push the cart every 5 milliseconds. Our task is solved if the robot can switch to each of the balance points when it's commanded to do so. But how do we tell the robot how well it's doing? In a nutshell, we give the robots rewards for good decisions and penalties for bad decisions, just like a teacher giving a grade to a student. This is called the reward function. At each step, based on the decision the robot made and the current state of the robot, the reward function computes, well, a reward, just like a single number, like a score in a video game. So at each step, the robot looks at its current state, makes a decision about what to do, and receives a reward based on that decision. We take all of those rewards the robot received and add them up. That sum of rewards is the final score in the game. It describes how well the robot did, and ultimately, that's the thing we want to maximize. There's something really important here. Notice that we're not just trying to maximize the reward we get at each step, we're trying to maximize the total reward we get across all of the steps. This might seem obvious to you, and honestly, it should. But this is one of the key insights of reinforcement learning. Essentially, our robots can learn to delay their gratification, which lets them achieve an overall better result than if it chose actions that gave it the best reward at each individual time step. This lets them learn really complex and counterintuitive behaviors that require the robots to plan way in advance.
Okay, when we first start training the neural net, it doesn't know how to do anything, and the pendulum just flops around. It might seem like this is useless, but this is normal for robot learning. When humans are learning something new, they start with an understanding of the world, and have an intuition for physics and a clear idea of what their task is. When robots are learning, on the other hand, they don't know anything. They don't know how to move their arms, or what their vision means. They don't even know what they're trying to do, really. So at the beginning, they just kind of flop around and try a bunch of things to see what rewards they get. At 10% into training, you can see the rewards have gone up, and the pendulum has already figured out the easiest of the balance modes, just letting the pendulum hang down. But when it tries to reach the other balance points, it's still just doing random stuff. We call this exploration. This is where the robot is just trying a bunch of stuff to see what sticks. It's getting closer to its goal, but it doesn't really know what strategy is going to work best yet. Just like for humans, exploration is important so that the robot sees all of the possible options for how to complete its task before it settles on one. At 40%, the robot is starting to make some real progress. It learns how to balance the pendulum all the way up, and at 60%, it figures out the up middle mode as well. It's now really getting how to do the motions correctly, and it's settling in on a strategy that seems to be really rewarding. But what do we do if the incremental progress stops working? This is where it really starts to get interesting. Robert's first try crawling to the cookies was so much more successful than even his 10th try walking to the cookies. So it's natural that he continued practicing only crawling because he was reaching the cookies. But no matter how good he gets at crawling, he'll never actually be able to grab the cookies without learning how to stand up. This is a dead end in the learning maze, so he has to go back to ground zero and learn how to walk. We expect rewards to drop while he's learning a new skill, because he's not making it close to the cookies. For the pendulum, it's actually gotten worse at the balance points it just perfected. But once we let them invest in their new skills, they can pull together all of their strategies to achieve the goal. At this phase of RL, the robots are switching from exploration to exploitation. They've settled in on strategies that work really well, and now they're focusing on fine-tuning the exact motions needed to achieve their goal.
Nice!
balance. Looking at the fully trained Pendulum, it can now reach the down middle balance point as well, and it can pretty seamlessly switch between all of them. This is remarkable because we are nowhere close to doing that. Here's a plot of the actions as the robot's moving. Every time it switches balance points, the actions become completely impossible to interpret. This is the crux of RL. The reward function, which is essentially our description of our task, was super simple. A reward function simple enough for almost anybody to intuitively understand resulted in a controller that competes with this insanely dense solution that scientists derive from fundamental physics. This isn't a joke. This is literally from a real paper. This is actually what it takes to control a double pendulum without reinforcement learning. That's pretty cool, but this is just the playground because the real world is full of problems that we don't already have good solutions to.
Okay, we now know enough to understand the shitting robots. When you as a human take a step, you're actually unstable for a second, just like the double pendulum. If your foot disappeared, you'd just fall over. You're relying on your foot to catch you, and the decision of where to place your foot and how to shift the weight to it and what to do if you made a bad choice is immensely complex. So instead of solving that problem, robot designers decided to choose a simpler walking algorithm by making the robots squat. When those robots take a step, they are keeping their torso completely level and square, and they're balancing on the foot on the ground, which means they're actually just never unstable. This lets the robot take its time to decide where to place its foot and correct it if it made a bad decision. You can feel this for yourself. Stand up and just start walking really slowly. You'll feel yourself want to bend your knees to give yourself more balance and control over the motion. The downside, of course, is that it's just way more tiring. The ability to stand up and lock your knees and swing your body from side to side saves so much energy. But now, with robot learning, we're finally able to get robots that are starting to walk like humans super efficiently. This innovation has opened the floodgates for growth in robotics. A bunch of humanoid companies are working on applying robot learning to tasks from packing boxes, to working on assembly lines, to doing your dishes at home. Self-driving car companies like Wave are using RL to help robots reason about how to drive around other human drivers. Nuclear scientists are exploring RL as an option to stabilize nuclear fusion power plants, and have actually learned new things about nuclear fusion based on the decisions that RL agents make. But the coolest thing to me is that this applies to more than just robots. RL is a general decision-making tool. It can be used to choose what words to say. OpenAI uses RL to train ChatGPT. Economists use math similar to RL to reason about the stock market. Google has used RL to make their data center cooling more efficient, which has saved them a bunch of money. And I'd be surprised if YouTube wasn't at least experimenting with RL to recommend you videos. RL has the potential to create robots and AIs that can make better decisions than we can, and it might hold the key to accelerating the rate at which we produce science and new technology. But before you get scared of the robot uprising, remember that our double pendulum hasn't even left our computer yet.
Michael, don't leave me here. Michael!
With the great power of RL comes a whole host of problems that make it hard to use in the real world. In the next videos, we're going to be exploring a bunch of those problems and working towards getting our robot dog walking around.